Lesson 2.2 is skills that you need. Operations with rational expressions. In your notebook on page 9, you have a whole bunch of rules for working with exponents. They are going to come in handy. Okay, you can review those on your own time. There are also a couple of other rules that you should be aware of. They have to do with multiplying and dividing, adding and subtracting fractions. Okay, so just very quickly, when you're multiplying, if you can find space for this, little notes, maybe at the bottom of page 9. Multiplying fractions, what's the strategy? If you have A over B times C over D.
You just do it, whatever you get.
Cross multiply.
No, you just do it.
Top times top, bottom times bottom. So it's AC over BD. Okay? So if you had 1/2 of x over 5. Okay? If you had half of x divided by 5, you'd have x divided by 10. Okay? 1 times x is x. 2 times 5 is 10. There's just a really simple example for us. What about dividing? Dividing fractions.
The inverse, or the second inverse.
Yeah, very good. So if you had A over B divided by C over D, that's equal to A over B, keep the first fraction the same, and then multiply by its inverse. Multiply by its inverse. That means flip it upside down. Okay? So that's AD, top times top, over BC, bottom times bottom. Another thing I just heard you guys say is cross multiply. That's another strategy. Start up here and cross multiply. A times D goes in your numerator. B times C goes in your denominator. Okay, that's a little cheat. As long as you do it the right way, then you'll be okay. Good. Adding and subtracting fractions. Adding, subtracting fractions. How do you do that?
You have to find a common denominator.
Good.
And then you only add or subtract the top.
Find common denominator. Then add / subtract numerator. Numerators. Keep denominator the same. Okay, so let's say we had x over 4 plus x over 3. You say, oh, those are x's. I can add those. They're x's. No. This chocolate bar is split into fourths, and this chocolate bar is split into thirds. You can't add them in any meaningful way and get an answer that is meaningful numerically. So what do you need to do? You need to express these things with a common denominator. Common denominator means the lowest common multiple of your denominators. So this thing I would express as a fraction over 12, and this one I'll express as a fraction over 12, and then we'll be talking about twelfths. And if I'm adding twelfths to twelfths, that makes sense because all the pieces are the same size. Well, how do I express x over 4 as a fraction over 12? Well, I need to find the equivalent numerator. If I multiplied the denominator by 3 to get 12, I need 3 x's. This now has the exact same value as this. I do the same over here, but this time my denominator got multiplied by 4. So I'm going to multiply my numerator by 4. And if I do the same thing to the top and the bottom, I've created an equivalent expression here. So this is the same as this, and this is the same as this, which means this statement is the same as this statement. Now that I'm dealing with twelfths, I can add them. I have 3 x's and 4 x's. That's 7 x's, and they are twelfths. Done. Yes?
Yes, sir.
Excellent. Okay, we're going to take those basic skills and just apply them to a whole bunch of different expressions, rational expressions. That's essentially what this lesson is. You're just going through a bunch of different problems and encountering different types of problems and applying those skills properly. So here we go. The first one that you have there, and when I copy it down, if you guys could just double check that I've copied down exactly what's in your book. I've got 4x squared over 3x times 12x cubed over 2x.
That's right.
So all I need to do here in my first step is multiply the numerators, top times top, and then multiply the denominators, bottom times bottom. When I do that, I'm paying attention to two things. I'm paying attention to the numerical part of each term, and then the variable part of each term. So we're talking about numbers first. 4 times 12 is pretty easy, 48. But now x squared, what does that actually mean?
X times itself.
4 to the power 2.
I have x times itself, so I have 2 factors of x. How many factors of x here?
3.
So I have 2 factors here and 3 factors here, so how many factors of x do I have?
5.
5, which is one way to think about this exponent rule, okay? It is the product rule of exponents. If you have 2 powers with the same base and they're multiplied together, x squared times x cubed, all you have to do is keep the base and add the exponents. Okay, that's written in that first page of notes for you. The denominator. Again, another rule that we can talk about is the commutative property of multiplication. That means I can, if I have 3 times x times 2 times x, which is what I have in the denominator, I can actually rearrange these any way I want and do 3 times 2 times x, which I can clearly see is 6x squared. Okay, and just another way of thinking about it. How do I simplify this?
Where do you divide this?
Yeah, look for common factors that I can pull out of the numerator and the denominator. I see 6 is a factor of both. So 48 divided by 6 leaves me with 8 and 1. And 5 factors of x divided by 2 factors of x. How many factors of x are going to be left?
5 over 2.
5 over 2x.
Okay, so we need a little bit of practice on the quotient rule of powers. Listen, this is now x times x times x times x times x. That's x to the power of 5. We can agree on that?
Divided by, oh, you just
Yeah?
released
We
it.
can agree on that?
Oh,
Is it just
yeah. So is it
And this is 2 factors of x. So cancel, 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 cancel. 3 left. Okay?
Can you have a
So
negative of
when
x?
you are dividing powers with the same base, you simply keep the base and subtract the exponent. Because this is now going to be over 1. The denominator is, sorry, that's not what I meant to do. This is now 3. Okay, the denominator became 1 times 1. Anything over 1 is just itself. So all I'm left here with is the numerator of 8 times x to the power of 3, 8x cubed. Okay, simplified. Okay, when I see that problem, this is how I would probably do it, but there is another way to do it that you might find easier. Can you think of what, I mean, if you see this, they're both rational expressions. You can just work with this as it is before multiplying it. So I can actually reduce before multiplying. What does that mean? Well, I see right here I have 2 factors of x divided by a factor of x. Well, that factor of x is going to cancel out one of those factors of x. What about over here? This factor of x is going to cancel out one of those factors of x. Okay? What else is happening? Well, this are both divisible by 2. So this factor of 2 is going to cancel out, I can pull out a factor of 2 from there as well. Okay? Oh, and now I see across the way here, I actually have a 6 and a 3, and they're both divisible by 3. And since it's just top times top, bottom times bottom, I can do that. I can kind of cross. Remember commutative property. This is 4 times x times 6 times x. And they're all can be shifted around however. They're all part of a group. So this factor of 3 actually cancels out that factor of 3. And then I can multiply. So now I have 4 times x times 2 times x squared. 4 times 2 is 8. X times x squared is x cubed, and there are no factors except for 1, like the factor of 1, left in the denominators. Okay, so you can multiply and then cancel, or you can cancel and then multiply. Your choice. You could cancel, and then maybe your brain didn't see that the 6 here and the 3 here actually cancel out. And then say you just go into the multiplication, then you realize you still have, 24 in the numerator and 3 in the denominator, and they're both divisible by 3, so you can do it then. Doesn't matter which order you do it in. Okay, as long as you reduce as far as you possibly can. Okay, and B says 10ab squared over 4a divided by 15a squared over 12b squared. What's the rule for dividing fractions? I'm going to flip it. Do I have to do that first?
No.
Probably should. It doesn't really matter. I would probably flip it first and then look for things to cancel out, but I could just sit here and start canceling things here and canceling things here. Okay, but the difference is I can't cancel things across anymore because this is not a top times top, bottom times bottom situation. Okay?
So when you flip it, you can't do cross multiplication?
Well, you could cross multiply it right now and then cancel out. You could definitely do that strategy right now. You could go 10ab squared times 12b squared, which is 120ab to the power of 4 over 4a times 15a, which is 60a cubed. Okay, you could do that. I usually rewrite it. Just helps me keep track of things.
Okay.
And now I can simplify. 120 over 60, that's really easy. I'm going to draw this line right away and just keep things in my numerator and denominator separated right away. 120 over 60 is 2. 2 over 1, but I don't need the 1. Then I look at my a's, and we're in that situation where we have more a's, more factors of a in the denominator than we have in the numerator. Well, this a is going to cancel out one of these. So I still have a squared in the denominator. And then factors of b, none of them get canceled out. So I have 2b to the power of 4 over a squared. Okay? That is fine. But now let's think about something. If we had to pay attention to restrictions, what would we say about both of these things? Because they both have rational expressions, and rational expressions are always going to have a restricted domain. So are there, let's look back at A, are there values of x that are not allowed to go into this expression? Basically, any value of x that makes a denominator equal 0, right? Denominators aren't allowed to equal 0. So what value of x would make this expression 0? 0. 3 times 0 is 0. 3 times negative 3, that's not 0. That's fine. That's negative 9. It's just a number. Okay? So I can't put 0 in this one. What can't I put in this one?
0.
0. Can I put negative 2 in it?
Yeah.
Yeah, I can. Can I put positive 2 in it?
Yeah.
Yeah. Okay, it can't be 0. So x can't be 0.
Is that going to be for all of them?
If you ever have something, if 0 ever causes the denominator to be 0, then yeah, it will be a restriction. But no, it's not more likely to be a restriction than any other number in the whole world.
Just so happens
Wait.
that it's for both of these ones?
That's just A.
0 is my favorite.
That's just A. So now we look at this one. Are there any restrictions here?
Yes.
Yep. What can't A be?
0.
A can't be 0. And there's another variable in the denominator. So pay attention. Even though B is not in the denominator by the time we're finished, it is in the denominator at some point. It's part of a fraction where it is in the denominator. Therefore, B cannot be,
0.
can't be 0.
Can't for now.
Good. In example 2, we have a similar situation. We're multiplying rational expressions still, but this time they have polynomials. There's not just one term in the numerator. You have a binomial here and a binomial down there. When we come to something like this, the first thing that we're going to want to do to try and simplify things is that nice word that starts with an F.
Factor.
Factor. Factor, factor, factor. Thank you. So factor wherever it's possible to factor. So I look at my first numerator. It's a squared plus 2a. I can factor an a out of that, which leaves us with a plus 2. Can't do anything to the denominator. And 20a squared I can't factor. It's only one term. But the denominator I can factor. 5a squared plus 10a. They have a numerical factor of 5. and a variable factor of a, which leaves me with a plus 2. Ooh, that's convenient.
Is it?
Now I can start dividing just by thinking about common factors, okay? Look at this in the numerator here, and I can do this because it's multiplication. Multiplication is commutative, so now I have this whole string of factors over this whole string of factors, which means if I see something in the numerator and in the denominator on either side, I can cancel them out. So here's an A and an A. They reduce to 1 over 1. Here is this factor. It's a binomial, but it's one factor grouped together, and I see it there and there. So they both reduce to 1 over 1. What about 20 divided by 5?
A.
That's going to be 4 over 1. And a squared over a.
Just A.
It's just going to leave an a in the numerator. So what's left? I have to look a little bit carefully, but I have 4a in the numerator. And I have
3a.
just 3
Oh, yeah.
in the denominator. So I have 4 over 3a, sorry, 4a over 3, or 4/3 a. And at this point, I also want to pay attention to the restrictions that we saw. So we didn't flip anything around, but the restrictions now, you have to pay attention. This one's, they are going to come from your factored step. It's a lot easier to see them in the factored step, and maybe it would be nice if I had found them before canceling everything out. But this one, you know, what can't a be? A can't be 0. Over here, it's a little bit more difficult to see, but you have a factor here and a factor here. What about this factor? What can't a be? A can't be 0, because that would cause the whole thing to be 0. What about this binomial factor?
Negative 2.
A can't be -2. Now, I did it a little bit. It'd be nicer if these were in numerical order. So when you're listing your factors on a test, you'll start from lowest to greatest, in which case -2 should be before 0. But there you have it. That is this expression simplified with the restrictions. Okay, this one's a little more challenging. It also is division. This time you don't just have binomials, you have trinomials, but the steps are the same. The first thing we're going to do, factor. If you can, factor. Okay, so we're going to factor everything that we can factor. And here we go. So what's common in this first numerator? 2x, which is going to leave us with x minus 4. Let's think about the denominator. It's a trinomial, so it's sum and product, but the leading coefficient is 1, so they made it pretty easy on us. Looking for two numbers that multiply to -10 and add to -3. -5, +2, so that's x minus 5, x plus 2. Okay, we're leaving that division sign in there. 4x squared can't be factored. This guy can be factored. Do it without calling it out, please. Two numbers that multiply to 20, add to -9. And check to see how you did. Okay, now I'm going to copy down the whole thing, but I'm going to flip my second rational expression here. So we've got 2x times x minus 4 over x minus 5, x plus 2 times, and then in the numerator we have x minus 5, x minus 4 over 4x squared.
I have a question.
Yep. So now we're going to look at restrictions first. Okay. So restrictions come from the denominator. What are they?
X. X cannot be 5.
X can't be -2. X can't be +5. And over here, x can't be 0. Okay, now I can start doing my canceling. I'm looking a factor of 2 in the numerator and denominator. Yep, that makes this 2. Factor of x. Yep, that makes this just x to the power of 1. What else? X minus 5 in the numerator and the denominator.
I appreciate that. No, you cannot.
And then, and that's as much as we can factor out, okay? So now what's left in the numerator is just x minus 4 times x minus 4.
Just 2x.
X minus 4 squared, good. You could do that. You could expand it. You don't need to though. That would be like going backwards. And in the denominator, I have a factor of 2 and a factor of x plus 2. And I'm going to copy down my restrictions. X can't be negative 2. X can't be 0. X can't be 5. And that one is finito. Okay, we caught an error. We missed the restrictions come from any denominator along the way. So I only did the restrictions from after we found the reciprocal of our second rational expression. But this is a restriction that needs to be included. X can't be 4.
I think so.
Example 3. Add and subtract rational expressions with monomial denominators. So they're giving us a easy start. Example 3, adding and subtracting, adding and subtracting. So we have 1 over 5x plus 1 over 2x. What has to be true in order for me to add and subtract fractions?
Common denominator.
I need a common denominator, which is finding the lowest common multiple of the denominator. So I'm going to do a little bit of work off to the side here. Yeah, the lowest common multiple is going to be 10x. How do we come up with that? Well, if I think about my denominator 5x, I think about the denominator 2x. The factors of this are 5 and x. The factors of this guy are 2 and x. And I need all the factors that they have in common. All right, sorry, I need to create a common factor. I'm saying the wrong words. I need to create a common denominator. So I need to look at all of the factors that are here and the factors that are here, and they need to be included in my new denominator. So my new denominator has to have a factor of 5, it has to have a factor of x, and it has to have a factor of 2, and it already has a factor of x. Okay? That's how you get the common denominator of 10x. We're going to do that again on the next one, so don't be so concerned that that was a bit quick. So what do I need to do? That means I need to rewrite 1 over 5x as a fraction over 10x. Well, I multiplied the denominator by 2, so I better multiply the numerator by 2. Now I have an equivalent expression. I do the same thing completely independently over here. 10x is going to be in the denominator. How did I get there? I multiplied it by 5, so I better multiply my numerator by 5. Now that we're talking about 10x's, I can add them. I have 7 of them, even though I don't know what 10x is. Are there any restrictions?
10, x cannot be a negative 10. Oh, 0. Oops.
X can't be 0. All right, in B, we have a little bit of a trickier one. Again, we're going to create a common denominator by finding the lowest common multiple of our denominators. So I'm going to do it the same way. In my first denominator, 2ab squared, the factors are 2a, b, and b. In my second denominator, 2b, the factors are 2 and b. Well, in this case, I need all of these factors to be a part of my denominator. What does that mean? Well, it has to have a 2 in it, it has to have an a in it, it has to have a b in it, and it has to have a b in it, and it already has a 2 in it, and it already has a b in it.
Could you use that step right there to cancel them out now?
2ab squared. And we're not canceling because now we're adding and subtracting.
Right.
Okay, so our new denominator is 2ab squared, which means my first term doesn't actually change at all because it already has that denominator that I'm aiming for. The second one, though, the numerator and the denominator need to be multiplied by, there's already a 2b there, but it needs to be multiplied by 2ab. See that? Those are the two factors that are missing from 2b. It's missing the a and the b. So I need to multiply the top by ab and the bottom by ab. So I'm just going to write that out step by step. My numerator then is b plus 2 times ab. And the numerator is, I can probably do that one right away, but I'll do it separate as well. 2b times ab. From here, we're going to distribute this AB to both terms in the binomial, and to this guy, this is all just multiplication, so that's pretty straightforward. Could have done it last step, but it's nice to see. My first one stays the same, AB squared plus 2. Then I have 2 over 2AB squared. And then my second term, the numerator. Watch what happens. The AB is distributed to the 2 and to the B. And it's multiplication. So B times A times B is AB squared. 2 times A times B is 2AB. And it's over, well, the goal was to create a common denominator. So I know it's going to be 2 times A times B squared. Okay. One thing that you really must pay attention to. I'm going to subtract the numerators, okay? One thing that might be really helpful to you is to rewrite this as a single fraction at this point. Because it has the same denominator, 2ab squared, I can rewrite it as ab squared plus 2 minus, but watch this, I have to have this in brackets. Why? Because this negative sign applies to the whole term, which means it's going to apply to this and to this.
Wouldn't it also apply to the 2ab on the bottom?
It applies to the whole term. If the negative was all of a sudden in the top and the bottom, you'd have two negative factors, which would actually be a positive. So no, it's only going to go in one place, and generally we put it in the numerator because it's cleaner, looks better, it's easier to work with. Okay, so what ends up happening here? Well, you have ab squared minus ab squared, which is 0. And then you have 2 minus 2ab. Okay? So let's write that. We have, right, these guys are going to cancel out. We have in the numerator, we have 2 minus 2ab. In the denominator, you have 2ab squared. And it looks like you should be pretty much done, but what do you notice?
Cancel out.
All the terms have a 2. Okay, there's two ways to think about this. If all the terms have a 2, you may do the same thing to all the terms. So I can divide every term by 2. That's fair. Okay? Another way to think about this is, and you don't need to write this step, but this is an easy way to think about it. You can actually factor the 2 out of the top piece. And now it's really easy to see that the factor of 2 in the numerator can cross out the factor of 2 in the denominator. And then from there, we're done. And the numerator is 1 minus ab. The denominator is ab squared. Mr. V, why can't I cross out this a and this a? And this b and one of these b's? Because these guys are stuck in a group. This isn't a and b. This is 1 minus ab. They're stuck in that group. So you can't just cancel out one thing from the binomial and cancel out the denominator. That doesn't work. Last thing we didn't do yet is restrictions. I'll do it quickly. Common denominator, a can't be 0 and b can't be 0.
Can't.
Okay, example 4, we are adding and subtracting rational expressions with polynomial denominators. So this time the process is the same. We're going to form a common denominator, but the trick is going to be in forming that the right way. So we have x plus 5 over x minus 3 plus x minus 7 over x plus 2. So again, if the denominators here were just, let's say, a numerical value, something like this, well, let me do something that's a little bit more challenging. Okay, what would we do? Well, we would need a common denominator. In this case, what would the common denominator be that we're looking for? 42. How did you get that?
6 times 7.
Yeah,
Common factor.
that's right. This has factors, lowest common multiple. So this has factors of 3 and 2. This has factors of 7 and 1. All of those factors need to be included in the denominator. And actually, the easiest way to get it in this case was just to go 6 times 7 is 42. We're going to use the same principle when we're doing these guys, okay? And again, the second principle that you're going to use then is you need this expression to be equivalent to that expression. So what becomes in the numerator of this 7x, okay? And over here, 6x over 42. Okay, so we're going to use that same principle as we're working with these binomial denominators. What does that mean? Well, if I need to express x plus 5 over x minus 3 and this guy with the same denominator, how do I create that denominator? I just multiply the two denominators together. So watch what happens to this first term. I'm going to draw my line. My denominator starts with x minus 3, but I need the denominator to actually be x minus 3x plus 2. Just like this denominator is 6 times 7. 6 times 7. This denominator is x minus 3 times x plus 2. Okay? Now, same process. I need to create an equivalent expression, which means if I did something to the denominator, multiplying by x plus 2, I have to do the same thing in the numerator. Multiply the numerator by x plus 2. Another way just quickly to think about this, if we multiplied this rational expression by x plus 2 over x plus 2, what did we really multiply it by? 1. Anything over itself is 1. Anything times 1 is just itself. So we have not changed the value of this expression at all. Okay, it's an equivalent expression. We've just made it possible to combine through addition with our next expression, which we're going to modify in the same way. So now we have x plus 2, and in the numerator x minus 7. And in this case, to get the same denominator, I have to multiply top and bottom by x minus 3, the denominator of the other term. Good job. That's going really well.
I don't understand.
Did you write some notes on this?
Yeah, that's a good idea. So
Maybe we should have said it.
multiply
What we just did.
multiply each rational expression. Multiply each rational expression by a fraction equal to 1. Multiply each rational expression by a fraction equal to 1. That will make each denominator x minus 3 x plus 2. Okay, multiply each rational expression. That's what we did. Here's our rational expression. We multiplied each of them by a fraction equal to 1. Notice that what we multiplied by isn't exactly the same. This one was x plus 2 over x plus 2, and this one was x minus 3 over x minus 3, but both of these are equal to 1. And the goal was to make the denominators x minus 3x plus 2. Well, you look at it and you say, oh, this one is x minus 3x plus 2, but this one is x plus 2x minus 3. Is that a problem?
No,
Yeah.
because it's commutative.
Multiplication is commutative. So these are exactly the same. 2 times 3 is the same as 3 times 2. And so you can do the same thing with this factor times that factor is the same as factor 2 times factor 1. Okay, makes no difference. Good? Now, at this point, we have a common denominator. which means we could express this all as one thing. Okay, x plus 5 times x plus 2 plus x minus 7 times x minus 3 all over x plus 2, x minus 3. Okay, we're going to do one more step before combining, and that is expanding, because actually here and here, both of these numerators have an x squared term. They both have terms with an x in it, and they both have a constant. So those things can be combined. Okay, so watch what happens. We don't have to distribute the denominators. They're fine as they are. Okay, we're just going to leave those alone. And actually, denominators in factored form are really helpful. Why? What do they tell us?
They tell us the x-intercepts.
Not the x-intercepts, but
The restrictions.
the restrictions. They tell us what x can't be. So that's really helpful. So if we expand this, I'm not going to spend a lot of time doing it. I'm just going to write what the expansion is. I've got x squared plus 7x plus 10. And the next one, try it on your own. Should get x squared minus 10x plus 21. And now, just like any other fraction, like if I were talking about fifths plus fifths, I could just add up my numerators, right? And it would still be over fifths. Same thing happens with this more complicated structure. I'm just talking about the denominator is the same. So it's over this plus over this, which means I can just add up my numerators. In this case, I have a addition there, which makes this pretty easy. If it was subtraction, like the next one, I'd have to distribute that negative sign to all the terms. I don't. I have x squared plus x squared. That's 2x squareds. I have 7x's minus 10x's. That's negative 3x's. I have 10 1s plus 21 1s. That's plus 31. And we know our denominator is x minus 3, x plus 2. What did we do there? We simply add the numerators. So it's all about taking your very basic algebra rules, not being overwhelmed, just relax, step by step. What can I do? What would I do if they were simpler numbers? Try to do the exact same thing. And restrictions come from all the parts of it, any restriction that we made along the way, starting from the original. And what are they?
X cannot be 3
or -2.
Good, x can't equal -2, and x cannot equal 3. Again, B, for example 4, is more complicated, but we're going to follow the exact same steps that we would have previously. Now, the difficulty with this one is in the denominator, you don't have a simple binomial. You have two trinomials. But do trinomials still have factors? Yeah, we could factor both of these, okay? So our first step then is going to be determine the lowest common multiple of the denominators. In order to do that, we're going to factor first, okay? So step 1, find LCM, lowest common multiple, of denominators by factoring them. I shouldn't have maybe written that so close. We're going to need some more space on our next line, or maybe 2 lines from now. But my numerators are just monomials. That's pretty easy. So I'm just going to copy this one down, x plus 9. And then I'm going to factor my denominator. I'm looking for 2 numbers that multiply to 48 and add to 2. That's 8 and 6, and the 8 is going to be positive. So I have x plus 8, x minus 6. Then over here, on my second term, we have the numerator of x minus 9. Now I'm looking for 2 numbers that multiply to 30 and add to -1. That's going to be 6 and 5, and the 6 is going to be negative. X minus 6, x plus 5. Now, look at what we have. They already have one common factor. but this denominator is missing a factor of x plus 5, and this denominator is missing a factor of x plus 8. So that tells me, remember, what am I going to do? I'm going to multiply both terms by a fraction equal to 1 in order to create a common denominator. So that means that this term, top and bottom, are going to get multiplied by x plus 5. That way I'll have all 3 factors that I need in the denominator. This term, top and bottom, are going to get multiplied by x plus 8. Then both of my denominators will be x plus 8 times x minus 6 times x plus 5. Does that make sense? So if I had left more space, I could do it right here in this step. I didn't, so I'm going to have to copy down my whole thing again. Sometimes it's easiest just to draw your line first. Over here, we said we're going to have x plus 9, which is what we have already, and we're going to multiply top and bottom by x plus 5. That will give us an equivalent expression and give us the common denominator that we need. In our next term, we're starting with x minus 9, and we're going to multiply top and bottom by x plus 8. That will give us the common denominator that we need. And from this step, I would right away write my denominators the same way. I know that they have the same 3 factors, and I know I can arrange those factors however I want to, because multiplication is commutative. So I would right away just write x plus 8, x minus 6, x plus 5, and that gets my brain past the common denominator part of solving this problem.
Why x plus 5?
So now I'm dealing with the same size pieces, you could say, right? Fractions, this is, you know, something split into 7 pieces. These are the size of my pieces. Anyway, but I notice a lot of my terms now in the numerator are trapped inside these binomials, right? I have x squared terms that could be combined if they weren't trapped inside this product. I have some x terms and some constants that are trapped, so I'm going to release them. And as I do that, I'm going to also do 2 steps. I'm going to combine them all over my common denominator of x plus 8, x minus 6, x plus 5. And there's one thing that I'm going to have to be very careful about, and it's the fact that I'm subtracting one from the other this time. So I have to keep them separate until I deal with that subtraction sign. So the expansion of the numerator of my first rational expression is x squared plus 14x plus 45. And once you get that down, take another look here carefully. I'm going to keep my subtraction sign, and my next expansion I'm going to keep in brackets. I have to do that because this negative sign applies to everything that I see in the numerator. So when I expand it, which is going to be x squared minus x minus 72, I need to be mindful that this negative sign applies to each of the terms of my trinomial. So what I would probably do if I'm just starting out is I would rewrite this. I would rewrite it with nothing changed here and then say minus x squared plus x plus 72. Okay, and actually we'll do that. Let's go ahead and do that. Once you get good at it, you can skip that step and do it mentally. But so we have x squared plus 14x plus 45 minus x squared plus x plus 72 over our common denominator of x plus 8, x minus 6, x plus 5. And now I can group like terms. So I'm going to draw my line. I'm going to write my denominator. And looking for like terms, I have x squared minus x squared. So no x squareds. Then I have 14x plus x, that's 15 x's, and plus 45 and plus 72, that's plus 117. Okay, this is the difference between the 2 original rational expressions that we got. What did we do? We factored the denominators, in order to find out which factors were missing to create a common denominator. When we realized that the first term was missing x plus 5 in the denominator, we multiplied top and bottom by x plus 5, not changing the value of the expression, but just changing what it looks like so that we could get a common denominator. Same over here, we realized we didn't have an x plus 8 term, so we multiplied top and bottom by x plus 8. Once they had a common denominator, we could combine them, and we expanded each numerator. Then we applied that negative symbol, distributing it to each of our terms in the trinomial, looked for like terms, simplified, and the last thing we need to do is note our restrictions.
So that's done.
Restrictions are x can't equal -8, x can't equal -5, and x can't equal +6. Try to do them in order if you can. Example 5, we have a bicycle relay. You have Raj and Mac. They're competing as a team in a 50-kilometer cycling race. 50-kilometer cycling race. So I'm just going to say, sure, 50 kilometers. Okay? There are 2 legs. That means each of them is going to take a leg, a part of the race. One of them is 30 kilometers. Leg A, 30 kilometers. Leg B, 20 kilometers. Okay? That's pretty straightforward so far. Assuming that each cyclist travels at a different average speed, so Raj and Mac, one of them is faster than the other one, determine a simplified expression to represent the total time of the race. Okay, so we need something to help us with a speed, distance, time situation. Yeah? So maybe you remember from any old science class or previous math classes, we need a distance, speed, time expression. T, yeah, the triangle, equals d over v. Okay? Distance equals time. Sorry, distance is time times speed, right? This is the triangle that you're talking about. So v is velocity. It's very similar to speed, but speed doesn't tell you which direction you're going in. Speed can never be negative, whereas velocity can be negative if you are moving backwards. So in this case, it's not going to matter. They're starting here. They're both moving forward. So you can think about it as speed. But in the case where something could be going forward or backwards, you can't talk about speed. It won't be helpful because you'll get the same answer going this way as going that way. And that would be, yeah, not helpful. Okay, so we're talking about velocity. D represents the distance traveled. V represents the speed. And then to calculate the total time, we just add the time that it takes for leg A and the time that it takes for leg B. So if the time for leg A is the distance of leg A over the speed of the biker and the cyclist, I guess I should say, and the time taken for leg B is the distance traveled over the speed of the cyclist, then we just add those things up, if that makes sense. So here we go. The total time, T, is going to equal TA, that's the time it takes to complete the first leg of the race, plus TB. Nothing too groundbreaking there, right? You complete one part and another part, and you add them up, and you have the total time. Now, we don't know, so now we're going to be using this formula for TA and for TB. What is the distance traveled in the first leg? 30 kilometers. So we know that the distance for T sub A is going to be 30 kilometers, but we do not know the speed of that cyclist, but we know that it's going to be the speed of the cyclist that does leg A, so V sub A. The time it takes for leg B to get completed is going to use the same formula, D over V, but specific for leg B. So what is the distance of leg B? 20 kilometers. And the velocity, the speed, we don't know, but it's going to be consistent for leg B. The cyclist who bikes leg B will go their speed. That's basically all this is saying, nothing new. So now we have the time it takes for the total in terms of the distance of each leg and the speed of each leg. And now we pause, and what do we have?
50.
A
Wait,
simplified
no.
expression.
We have a rational expression being added together. They're fractions. What do we need when we're adding fractions? Common denominator. The common denominator. The denominator here is v sub a, and the denominator here is v sub b. All that means is this is a value, and this is a value, but we don't know what the value is. So you could kind of think of this as x and this as y. And in order to get a common denominator, you'd need a common denominator of xy. Does that make sense?
Yes.
Multiply the denominators together. So that's what we're going to do. We're going to have to multiply the numerator and the denominator of each term by a fraction equal to 1 in order to get a common denominator. The common denominator that we want is VA, VB. And if we multiplied the denominator by VB, we have to multiply the numerator by VB. It's a bit scary because they're weird little symbols, but we're really doing the exact same thing here as we were doing before. In our second rational expression, we want a denominator of VA, VB. In order to get that, we had to multiply the denominator by VA, so multiply the numerator by VA. And again, it looks messy, but you're going to think back and say, okay, now what can I do? Well, now that I have the same denominator, I can combine the numerators by addition. So in numerator land, I have 30 times VB plus 20 times VA, and it's over VA, VB. That is a simplified expression to represent the total time of the race when we don't know who biked each leg and we don't know how fast they were going. Okay? In B, what makes sense? Is the faster person going to do leg A or leg B?
Leg A.
Faster person is going to do leg A. Okay? So Raj can maintain an average speed of 35 kilometers per hour. Mac can do an average speed of 25 kilometers per hour. And we need to determine the minimum time for them to complete the race. So who's going to do what?
Raj is gonna do A, and then Mac is gonna do B.
Raj is going to do A, and Mac is going to do B. And that means I know, so I know that the velocity of A is going to be Raj's speed of 35 kilometers per hour. And the velocity of leg B is going to be 25 kilometers per hour. Okay, I wrote those down first because now it's pretty easy to just sub them in to our equation. And remember, we're dealing with t is equal to, in the numerator, it's 30 times the velocity of the second leg, which is 25, plus 20 times the velocity of the first leg, which is 35, all over the product of the velocities, 35 times 25. And if we carefully put that into our calculator, you end up with 1.66. What does that mean? T equals 1.66. Well, our measurements are in kilometers per hour. So it's going to take them 1.66 hours to complete this race. Therefore, it will take the team 1.66 hours. Do you guys know, could you translate that into hours and minutes? Two-thirds, this is 2/3 of an hour. So 1 hour and 40 minutes. 1 hour and 40 minutes to complete the race. That's the fastest they could do it. Now, if they switched their order, they'd have a higher time. They'd have a worse time. Good. Your practice problems for that section are found on page 94, and they are numbers 1 through 9. Page 94, numbers 1 through 9.
Is this page